Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're taking our first step into the world of A3C. And as a first step, we're going to find out what this abbreviation stands for. So A3C stands for Asynchronous Advantage Actor-Critic Algorithm. This is an algorithm which was developed at Google DeepMind in 2016 by a group of researchers, and it's the cutting-edge algorithm for artificial intelligence to date. Now, it has multiple modifications, and we'll discuss that more in the course, especially in the practical tutorials, but nevertheless, this algorithm blows everything else, including deep convolutional Q-learning networks, out of the water, completely out of the water, and it is faster, it takes less time for training, and gets better results. So throughout this part of the course, we'll be referencing, and we have already referenced, but we'll be referencing even more, a paper, or the paper that was published that first introduced A3C. It's called Asynchronous Methods of Deep Reinforcement Learning by Vladimir Mnych and others from Google DeepMind. So I'm going to show you this paper now so that you have an introduction to it. So here is this paper. I wanted to show it to you so that you can get a feel for it and already get introduced to it a little bit. And of course, it is highly recommended to read through the paper and understand what exactly they're talking about. And you'll see that throughout the practical tutorials, Adlan will be taking you through certain parts of the paper, through certain paragraphs or sections which will be relevant to what we'll be programming at that point in time. And what I wanted to point out here is, like, as you can see, a lot of research went into this, and there's a lot of references as well. But like a part that I really like is that at the very end, they compare the different algorithms, compare the results. And this is what I wanted to point out here. So let's zoom in a little bit. So here, as you can see, even in Google DeepMind, they're training or they're evaluating the algorithms on games, just as we're doing in this course. So exactly the same principle, because games are a simulated environment or a small environment, a confined environment with certain rules, and they want to understand how well this artificial intelligence is doing in those games. And here we've got exactly all those games which you can find. A lot of them you can find on OpenAI Gym, and the games that we've been working with. So for instance, in this section, we're working with Breakout, so it's also here. And so you can see that for Breakout, they've got in bold, they've got the best algorithm highlighted. So DQN, that's the algorithm we've been working with. Then some other algorithms, and then here you've got A3C with an LSTM, long short-term memory. So that's the one we'll be implementing in this part of the course. We'll have A3C with an LSTM, which makes it even stronger. So as you can see, Breakout is the best result is achieved by A3C with LSTM. So that's the score, 766.8 compared to the others. And also you can see that for the most of them, so if we now take like a bigger picture view, you can see that most of the bold ones are actually in this last column. So yes, indeed, there are some games where other algorithms are performing better. But as you can see, DQN is actually not performing better in any of the games. But you can see that there are other algorithms perform better sometimes, but A3C LSTM performs the best in most cases. So you can see that this is bold, this one, these ones, this one, and so on. So you can see that A3C LSTM is a really powerful algorithm. It is indeed at the forefront of artificial intelligence, and that's exactly what we'll be implementing. So very exciting section ahead. Highly encourage you to go through this paper and get a feel for what we're going to be talking about. And then throughout this section and throughout especially the practical side of the things, practical side of tutorials, we're going to be going through this in detail. We're actually going to be working with their pseudocode here, which is available, and so Adlan will show you how to implement that and how we're going to be working with that. Hello and welcome back to the course on artificial intelligence. Today we're talking about the first part of A3C, the Actor-Critic part. So here we've got Asynchronous Advantage Actor-Critic algorithm, and we're going to be talking about that underlined Actor-Critic part. That's where we're going to start. You could technically start anywhere, but it just makes a lot more sense to start from Actor-Critic, because that way we'll have like a very consecutive explanation of or intuitive understanding of what's going on. It's going to facilitate us better if we start surprisingly at the end of this abbreviation. All right, so far in this course, we've come up with deep convolutional Q-learning, which is illustrated over here. So we've got the computer seeing the pixels, so the actual image in pixels, not just a vector. So it's not cheating. It's actually seeing exactly what a human sees. It sees the monsters, it sees the health, it sees the parameters at the bottom, it sees the corridor, it sees the gun. It sees exactly the same thing as a human would see when playing this game. Then that image is passed through a convolutional layer. Then it's passed through a pooling layer, then it's flattened and goes into a neural network. And then at the output, we've got actions. As you remember, we've got those Q values. Then we apply a action selection policy to them. So for instance, we apply a softmax and we find out which action we want to take. And so there's some exploration plus exploitation going on there, a combination of the two. So that is how deep convolutional Q-learning works. But now let's see what we're going to do with this. So for simplicity's sake, just so that it's easier for us to operate with this, because we're going to be adjusting this image and moving it around, we're going to replace the circles with squares, with these rectangular boxes. And we're also going to get rid of those lines in between, just change them to arrows. So this doesn't change the essence. This is just the representation on this chart. This is still, even this representation is still deep convolutional Q-learning. It's just going to be easier for us to modify it and show exactly what A3C is. So that's just how we're going to represent things from here. And what A3C does, or this specific part, so we're starting, remember, we're starting like step by step. We're starting with the actor-critic part. So we're going to see how we go from deep convolutional Q-learning to A3C step by step. And first step, we're going to introduce this actor-critic part over here. So we're going to talk about that. So the first thing that happens is this last bit, the output, is actually, we're just going to redraw it like this. So it's exactly the same output, exactly the same Q values, or exactly the same actions. So if you had 8 possible actions, you still have 8 possible actions. We're just going to put them at the top so they take up less space. So far nothing has changed. So far this and this are exactly the same. But now this is where the actor-critic part comes in. We're going to have a second output. We're going to have so the first one is a set of outputs, and here we're going to have a separate individual output. So technically we're going to be using our neural network. So once the image and everything, like the values go through the network from left to right over here, they don't just spit out one set of values, they spit up actually 2 sets. And so the top set, we already know what it is. It's the possible actions, but here we're actually going to have another extra value. So let's have a look at that. What is that value? So here we go. That's the top. So we just kind of like reduce the size of this illustration. The top output are the Q values, as we discussed previously, for the actions. So there, same thing, everything is same. But then now this bottom part, and the top part is actually called the actor. We're going to give it a name. That's the actor because that's the part where the agent chooses what it wants to do. So that it's like it's acting, it's as if it's performing on stage. And it'll make more sense once we have the second name up on the screen as well. And then the second output is just like one value, and that is V of S. So that is the value of the state. So if Q of S and A is the Q value of a certain action, and as you can see, that's why there's action 1, action 2, action 3, up to action 6, or however many actions there possibly are in that state. So in a given state S, what is the Q value of taking action A, action 2, action 1, action 2, and so on. Then here we're also using the neural network to predict what is the value of the state we're actually in. And this part is called the critic. And so that's the intuitive, or the kind of not even full intuitive, that's just like the start of the intuition behind actor-critic, that there's 2 outputs now from the neural network, not just one. Before we just had that one output, which we now call the actor, but now we have 2 outputs, actor and critic. And there's going to be a dynamic between them, which we'll explore further. But for now, it's important to understand that we're predicting not just the Q values of the actions that the agent can take from this certain state, but we're also predicting the value of being in this current state using that same neural network. So that's the core of the first step into the actor-critic. And now we're going to need to talk about asynchronous, which we'll do in the next tutorial, in order to understand exactly what's going on between the Actor-Critic. And the final thing for today is that all of these Q values, as we know, that's also called policy. So in some literature, in some blogs, in some discussions you might find in the Actor-Critic, you might find the author talking about Q values on this side of the actor. In other literature and blog posts and discussions, you will find the author talking about the policy. So, and usually it's they use a Greek letter P for representing the policy, or it might just say policy of state S. So altogether, these are the policy of state. It's because, as we remember, the policy is if you put all the actions together, the possible actions, and then it's deciding which action to take. So these are going to be like the probabilities of taking each action. So that's the policy. So don't be thrown off if you see one or the other. They basically mean the same thing. So on one hand here, you've got the policy or the Q values. On the other hand, you've got the actual value of the state, and they're being predicted from the neural network. Hello and welcome back to the course on artificial intelligence. Today we're continuing our journey into the world of A3C, and we're talking about the asynchronous side of A3C. So there we have our abbreviation, Asynchronous Advantage Actor-Critic, and today we're going to find out what asynchronous here stands for, what it means. And let's go back a step. Let's look at what we started this whole course with. We started with reinforcement learning and what it's all about, that the agent is in a certain state. They observe the state, they make certain decisions, they take actions in that state, and then the state is changed, so they get into a new state, plus they get a reward. So they get a reward for taking that action, or some sort of reward, which could be a penalty as well, and they end up in a new state. And based on that, now they take another action. Again, they get a reward, and end up in a new state, and they take another action, and so on. And so that is the basis behind all of reinforcement learning, and that's what we've been using in Q-learning, in deep Q-learning, in deep convolutional Q-learning, and that has allowed our agents to beat gradually more complex environments. But now we're going to introduce a better concept and even further take this even to a further level. What A3C introduces through this asynchronous element is, instead of having one agent attack the environment, they have 3 agents, or whatever number of agents. So several agents attacking the same environment. And the key here is that why it's called asynchronous is because they're initialized differently. So their starting points are different. So for instance, as you'll see from practical tutorials, you set a random seed and you set it differently for each of the agents. And that way, because their starting points are different, they're going to first go through environments in different ways, and then they're going to explore in different ways. And then in the next iterations, they're also going to explore in different ways. And so, for instance, if you have 3 agents, all of a sudden you're getting triple the amount of experience. Instead of just one agent going through and exploring the environment and trying to understand how to operate in that environment, you now have 3 or however many of them going through that, getting this experience. And so that each one of them is learning through this bigger experience. And apart from being just giving a broader range of experience, it also reduces the chances of one agent getting stuck in a local maximum. So for instance, if one agent finds like a way to beat the environment, which is not the most optimal, because if it deviates to the left or to the right from that solution that it found, it always gets more penalized. It might get stuck in that local maximum. It might just keep doing that, thinking that that's the optimal solution where it's actually not. Well, the likelihood of several agents getting stuck in that same local maximum decreases with the number of agents. So the probability of one agent getting stuck in a certain local maximum might be high, or might be a certain value. But the probability when you have 3 of them, of all 3 of them getting stuck in that local maximum, is much lower. And as long as they share experience between each other, they can help each other out. So if one of them gets stuck, for instance, it's stuck in a local maximum, just simply think that's the best one, that's the best solution all the time, and keeps doing that. Well, as long as it interacts with the other agents, so let's say this guy gets stuck in a local maximum, as long as it interacts with the other agents through the way we build our whole algorithm, A3C algorithm, they will help him out. They will give him knowledge that actually, no, hey, you should explore this, or he will be more likely to get out of that And also overall, the environment will know that, hey, even though this is a great maximum, these other agents have seen better options, and we should keep exploring because they looks like they're better options. So in a very short, kind of rough, intuitive understanding, those are some of the advantages of having these asynchronous agents. First of all, you like have more experience to choose from and to learn from. You could get to the solution faster. And generally speaking, there's a lesser chance of getting stuck in a certain local maximum. So let's see how this all plays out in this model that we've built so far. So as you remember, this is what we've gotten so far through the Actor-Critic. And this is like where it all ties in. This is, so far, as you remember from the previous tutorial, we did introduce this, we had this already, even in deep convolutional Q learning. So we just named it Actor now. But now we've introduced critic, but so far it doesn't really make sense. What's the point of having this critic and measuring the value of the state, or predicting the value of the state using the same neural networks, this same approach? But now this is the part where it's going to start making more sense. What we're going to do is we're going to replicate this, because now we have multiple agents. So with multiple agents, this is what it would look like. So the first way of imagining it is now we have these three things. Well, remember what we said about them sharing the experience between each other. So this is actually right now they're all independent. You have one playing the game, another one playing the game, another one playing the game. It's like launching your agent on 3 different computers. You put 3 different computers next to each other and you launch them, and that's great. Like, indeed, you'll get more experience, you'll get like more variety, especially if they're initialized different. So we're gonna assume from here that they're always initialized different. Even though we have the same picture here, we're going to know that they are actually initialized differently. So it's not going to be like identical training, identical learning from this game. And so even if you put 3 computers side by side and you launch them, yes, you're going to have more experience because you're going to have 3 agents playing, and also you're going to have a bigger variety of possible solutions. So that's true. But the problem is that they're not sharing that experience among each other. They're not learning from each other. So they don't have that synergy. They don't have the advantage or the extra power that they would get if they were cooperating. Like how if you have a team of people, they work better together than each one of them separately. So like in a team, here you got 1 + 1 + 1, it's 3. But in a team, 1 + 1 + 1 is not 3, it's like 33, because they leverage each other's strengths and mitigate each other's weaknesses. And same thing here. So if you put these 3 computers side by side, yes, you'll have more experience, more variety, and possibly someone will get to a better solution than the other one. That's great. But it'll be even better if they start sharing that experience. And how do they do that? Well, it's through this V that we calculated. So this V value that's the output of our network is actually like that. So they have this same V. So every time all these agents, they're contributing to the same critic. They don't have separate critics, they have a common critic. And that's the key of how the Actor-Critic ties in with the Asynchronous. So there's one critic that's watching as they get experience. So how do we calculate the V? We calculate the V through, as you remember, we calculate the V through the values that we get. So the rewards that we get through the environment. And so as the agents explore their environment, they're predicting the V, plus they have the V that they can calculate. This is all ties back into what we've already discussed in the previous sections of this course. So they already have a V that they can predict, expect through the rewards that they know that exist in this maze, and that they've already explored. And as they explore them, of course, that value can change. But also they have the V this V is the output of the neural network. So as they're going through this, they're going to be adjusting their neural networks in order to better match that expected V. So basically, this is shared. The critic part is shared between the agents, and that is how they share the information between each other. That's how they are able to kind of see what's going on in the environment, share it with each other, and then use that, as we'll see further in the next part, in the advantage, use that in order to optimize how they're behaving in that environment. And the other thing to note here is, so this was A3C. This is like the core of A3C up to here. This is a version of A3C. But there's an actually even better implementation of this A3C, which you'll actually hear Adlan talk about in the one of the first tutorials in the practical side of things. And what he'll be talking about is how the creator of PyTorch actually made an adjustment to one of the codes that was shared on GitHub, where he took all of these. As you can see right now, they have separate neural networks and only they share the V. That adjustment that was made was actually to take all of these neural networks and put them into one, take them and put them together. So ultimately, there's only one neural network here shared among the agents. So before they had, each one of them had one neural network, which was shared for the actor and for the critic, one neural network shared for the actor, for the critic, one neural network shared for the actor, for the critic. Now they all have one neural network, which is shared for the actor, critic, actor, critic, actor, critic. And then the critic is here in common. So let's see, let's move these pictures to the left over here. So make some space. And this is basically the architecture or the structure that we're going to be using in the practical tutorials. I know that like this may sound a bit overwhelming at this stage, but we've got one more A to talk about, which is the advantage, and there we'll see a bit better in action how this is going. So we'll talk about the intuition in action there. But generally speaking, this is what it is. There's one network which each of the agents use. So they share, basically what that means is that they share the weights. The weights of the network are shared between the agents. And when they update the whole network, not just their own network. And then they have outputs. They have like these actions for each agent, and then they have the critic that is shared, which is going to be monitoring. So I know all of this is kind of like there's a lot of stuff right now, but hopefully it's slowly coming together. At least the main takeaway from here is that the critic, because it's shared, that's how the agents are able to make sure that they're cooperating together in order to get to the result much faster. And then in the next tutorial, we'll see even further how all of this adds up, how all of this comes together. And for now, there's we would like to recommend you an additional reading. So this is a blog by Jaromir Janisch. It's called Let's Make an A3C Implementation. There's actually two parts, implementation and theory. There's the link, and it's very similar to what Adlan will be implementing in the practical side of the tutorial. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're talking about the final A in A3C. We're talking about advantage. So there it is. We've already spoken about Actor-Critic and Asynchronous previously, and slowly built our way to what we're going to be looking at today. And with advantage, we're going to put everything together. So this is what we have so far. We've got a neural network which is shared between the agents, the asynchronous agents, and then we've got the critic, which is also shared between the agents. So how does this all play out, and why is this critic shared between the agents? Let's have a look at that. Well, understand this better, we're going to look at an example. We're going to look at this agent, for instance, and see what happens when he's in a certain state and he needs to make a decision what action to play. So this agent is in a state, he sees this image, and then what happens is this information goes into the neural network, it goes to the convolutional layer, then it goes into the pooling layer, then it goes into the flattening layer, and then from there it goes into the hidden layers of the neural network. And then as an output, he gets all of these policy values, the QU values of the policy, and also he gets the V value, the critic value. And so, as we know, neural networks, in order to operate, they need to propagate certain errors or losses back through the network, so this way, in order to update the weights. So what losses are we going to be dealing with here? Well, we've got two losses. We've got the value loss and the policy loss. So the value loss is linked to the V value, policy loss is linked to policy. And so value loss, we've already dealt with it before. We know that we have rewards, and we know that we have a discount factor. So basically, this is very similar to what we were talking about in the deep Q-learning tutorials. Basically, the network predicts a certain value V, and at the same time, we can estimate what should be, based on what we know about the environment so far, we can estimate what should the value V be in the state. And by comparing the two, we can calculate the value loss and then backpropagate the network, update the weights. So that's pretty straightforward. The new thing here is the policy loss. And so what is this policy loss and how does it work? Well, this is the part where this whole situation where the critic is shared between the actors or between the agents is going to finally emerge. So to understand policy loss, we need to introduce a value called advantage, hence the name of this part of this tutorial and this whole part of the A3C algorithm, the advantage. And the advantage is calculated as Q of S and A minus V of S. So basically, the Q value that you chose to play of the action that you chose to play in the state that you were in, state S, minus the value of that state. So this is the difference between the two, and that is called advantage. And the advantage is used in the calculation of the policy loss. Now, we won't go into the formula of the policy loss calculation because it's quite complex. It uses entropy, or it can use entropy, doesn't have to. We're not going to dissect that formula, but we're going to understand this on an intuitive level. Why are we doing this? Why are we calculating this advantage, and how is it going to help us? Well, let's look at this for a second. The Q value here comes from what the neural network predicted for this agent. So it predicted in this specific action, in this specific state for the action that it can play. So it's got these actions, and it can select one of them, and it can play it. Well, whereas the V value is the value that is dictated by the critic. It is the value that we have here in this shared part. And that's the key here, that this part is shared. So the critic, because this is how the critic comes into play, because we've got a value that we choose, or the action that we choose to play for this agent in that state, but then the critic can tell us what is the known value of that state. What is overall the known value for this whole group of agents that are performing together, because they're sharing, not necessarily because they're sharing the network, but because they're sharing the critic, they're all contributing to these V values that are being calculated for a different state. So the whole A3C algorithm says, okay, so the critic knows a V value. How much better is your Q value that you're selecting compared to the known V value? That's what it's saying. So that's basically it. So that, okay, I'm going to select a Q value here based on my policy, based on whatever we use, like a softmax function or a epsilon greedy policy or something like that. And of course, there'll be exploration plus exploitation combined in there. But we select a Q value, and now the question is, what is the advantage? Hence, it's called advantage. What is the advantage that your selected action brings compared to the known value of that state? And that is the essence of the advantage. And basically, then that is used to calculate the policy loss. And then the policy loss is then backpropagated back through the network. So they're both backpropagated through the network, and the weights are adjusted in order for the network to better represent the value of the critic. And also, so that's this top part. But then this also part, the key here is that the weights are when this policy loss is backpropagated, the weights are adjusted in such a way so that this advantage is maximized. So like that's the intuitive side of the intuitive understanding of it, that we are backpropagating this policy loss through the network in order to help maximize this advantage. And what that means is basically that when an agent comes across bad actions, like actions where the Q value is less than the known value for this state. So basically the whole A3C algorithm knows that the value for the state is something, X. And then all of a sudden you came across a very bad action, and you chose a bad action. And what that means for the A3C algorithm means that, well, why would we do something like that when it's worse than what we already know about this whole environment and what we could have done? So we shouldn't do more of that. And therefore the weights are adjusted in a way so that happens rarer, so that happens less rare. So that's a less frequent occurrence that we choose that bad action. On the other hand, if you choose a very good action where Q value is greater than V or much greater, then during this backpropagation of the policy loss through the network, the weights are going to be updated in such a way to reinforce that, to reassure that to happen again, so that the weights will be adjusted in such a way so the A3C algorithm will think, oh wow, that was really cool. The advantage was very high there. I should do more of that, and therefore it will update the weights in such a way that will be more likely to occur in the future, that action. So, and therefore that is, that's how the network is slowly going to adapt and slowly going to construct itself into something that on one hand calculates the value correctly, and then on the other hand, or as correctly as possible, and on the other hand, it encourages, or it has actions which have a high advantage. So there we go. That's this part. And now let's have a look at another one just to kind of reinforce what we just discussed. So let's look at the top one. So same thing here. The top agent sees a situation, a state is in a state, and then needs to decide what to do. So sends this information to the network. So this image goes into network, goes to convolutional layer, pooling layer, flattening layer, goes into the hidden layers. And then from here, we get an output. We get the Q values of the policy. We get the V values. Again, same thing. We've got two losses. We've got the value loss, which is here, policy loss, which is here. Value loss, we already know how it's calculated. We discussed this in the deep Q learning and just discussed it just now as well. So that's how the value loss calculated. And then the policy loss, again, in order to calculate that, which we're not going to go into formula, but on an intuitive level, we're calculating the advantage, which is, okay, so we took a certain action, we chose a certain action based on our selection policy, whether it's softmax or epsilon greedy or whatever other selection policy that we're using. And then what's the action we took? Now let's compare it to the known value of the state, which comes from the shared critic. So this critic is kind of like, if you think about it, he's kind of observing all of these agents at the same time. He's looking at this one, looking at this one, this one. They're all contributing towards the critic to get the critic more up to speed with the environment, to make sure that the critic is representative of what's going on in the actual environment, so that the weights, that's where the value loss comes in, so that the weights of the actual neural network, that they reflect very well the actual situation of things in the environment, so that they can then rely on this value and then use it here. And so basically, so all of these agents, agents are contributing to this critic, but then at the same time, through this value loss, but at the same time, the critic is observing the decisions or the policies of these agents. It's like looking back at like I'm trying to draw like an arrow to the policy, an arrow. It's looking back at them, at the decisions that they're making. It's criticizing these decisions through the advantage. It's saying, okay, you made a decision, you chose this action. That's great. Now let's calculate the advantage. What is the advantage? The advantage is A equals, the Q value of the decision I made, or the choice I made, the action I made, chose to take, minus the known value to the critic, So calculate the difference. If it's a low difference, when your policy loss is backpropagated through the network, the weights are going to be adjusted. It's going to encourage the weights to be adjusted in such a way that doesn't happen again. That Q value, or that Q value is going to be lower, so that because our policy selects the actions based on the Q values. The higher the Q value, the more likely it's going to be selected. So if we were using like an argmax policy, then we'd just always select the one with the highest. As you remember, we discussed this. Then we'd always select the one with the highest Q value. But we're using a probabilistic approach, where either using like softmax or epsilon greedy policy. And then, so we're basically selecting, we can select any one of them, but the higher the Q value, the better. So if we selected something and then the advantage was very low, then bam, the network is going to be updated in such a way that next time this Q value of that certain action is going to be less, and maybe something else will be more. So that's how that is played out. And on the other hand, if we select something where the advantage is going to be high, then this is going to go into the policy loss, and then the network is going to be updated. So that is a more commonly observed scenario. And so basically, this whole policy loss helps the network adapt or morph in such a way that we do more of the good stuff, good actions and good things, and do less of the bad things. And that's how these two losses come into play, and that's how they backpropagate. So hopefully that clears up in a very intuitive way. Of course, we didn't go into the formulas, into the complex mathematics behind all of this, and like into the very intricate details. But at the same time, hopefully in an intuitive way, all of this clears up why we have the actor and the critic and how they interact together. That, you have these agents asynchronous. So this is the synchronous side of things. Then this is your actor and your critic, and this is your advantage, and how that all comes into play. So these asynchronous agents, they're they're playing this or exploring the environment and working through the environment, and they're all together contributing to a critic, which is then observing their policies, observing the actors, which is what this is called, and through the advantage, and therefore coming up with this policy loss, and then policy and value loss, they're back propagated to adjust the network in order to, on one hand, represent the true way of things in the environment, on the other hand, to improve the actors' performances. So there we go. That's a quick recap of the intuition we discussed. And once again, hopefully this is all coming together on an intuitive level. And of course, in the practical tutorials, we'll talk more about how all of this works, and Adlan will walk you through the process of building this. But having this image in your mind and this kind of like a roadmap of everything, how it comes together, should be, I hope, it will be very helpful for you to better navigate the practical side of things. And in terms of additional reading for today, we've got two elements. So first one is on the advantage. So here we've got high dimensional continuous controlling using generalized advantage estimation by John Schulman. And this is an image of a stick figure getting up, like standing up. And here you can find even more about advantage, and you'll find out the different types of advantages. So you've got the generalized advantage estimation. You've got advantages that you use actually in the formulas, in the calculation. So if you want to find out more about advantage and exactly how it works, the formulas behind it, and some of the top elements or formulas and know-hows in the space of this advantage that we discussed, then this is the article to go to. And one other element that or piece of work that we wanted to remind you about is a series of blog posts by Arthur Giuliani, which we've mentioned a couple of times already. This is part 8, which is specifically about A3C. So here you can get another explanation, so with a bit more mathematics about what's going on, and maybe you can pick up some additional things from here. Just two things to keep in mind. First of all, as always, this blog is in TensorFlow, whereas we're using PyTorch, so keep that in mind. And the second thing is that the way we structured our approach is we talked about Actor-Critic first, then we talked about Asynchronous, and then we talked about advantage. Whereas in his blog, Arthur first talks about Asynchronous, then Actor-Critic, then advantage. So keep that in mind. So hopefully that doesn't throw you off. But other than that, of course, it's a great piece of content, and we do highly recommend checking it out for some additional information. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.